Hi, I'm very excited to give an invited talk here at ICAPS, and many thanks to the organizers for pulling off this virtual conference. I know it's a lot of work. So before I get started, I would like to mention that my slides are available at www.automl.org/talks, and all the references throughout are hyperlinks that you can click to actually get the PDF. So you can download the slides, follow along as you listen to the talk, and when you want to get more details on a slide, then there's typically a reference where you can directly get the paper. So this talk is all about getting the most out of your planners. And what that means can be summarized in this one slide here. So algorithm configuration, which we'll be talking a lot about today, finds good settings of your parameters. This is of course useful because nobody really enjoys optimizing their hyperparameters by hand, in particular not, for example, on a per domain basis. But algorithm configuration is still very limited. It only finds a single fixed parameter setting, and it can't adapt, for example, to the instance at hand or to the search progress and so on. And in this talk, what I want to do is propose dynamic algorithm configuration, DAC, which basically can take some state features, and then, well, you have this agent, Mr. DAC, and that chooses the right parameter setting for these state features at hand. And those state features could include information about the instance that you're solving, the search progress, the time, etc., etc. So there'll be two parts to the talk. The first one is, well, actually an overview about previous work on meta-algorithmic approaches, namely algorithm configuration, and also some about algorithm portfolios. And then the second part is about dynamic algorithm configuration, which actually we'll see generalizes both algorithm configuration and portfolios. This work is based on papers with several people. In particular, the first part is goes back to work that I've done in my PhD with Holger Hoos and Kevin Leighton Brown at UBC. And the second part is on dynamic algorithm configuration. That's work mostly done in Freiburg and our extended group there. So it's mostly done with my PhD student, Andre Biedenkap, and my previous postdoc, Marius Lindauer, who is now a professor at the University of Hannover in Germany. And the planning part here is also chiefly includes David Speck, who is the first author of a paper on DAC for planning that I'll be talking about, and Robert Mattmüller, both from the AI planning group in Freiburg. The extended team of people working on DAC in my group includes my postdocs, Noor Awad and Stephen Adriansen, and my student, Reza Shala, and my previous master student and now Marius's PhD student, Teresa Eimer. So let's get started with algorithm configuration. The algorithm configuration problem is as follows. So we are given an algorithm that has a configuration space and we have some training instances. And then we ask a configurator to find the best parameter setting of this algorithm on these training instances. And then it spits out this optimized configuration, and then at test time for new instances in an online application, it's just used directly, the algorithm is used with this one optimized configuration. So a bit more formally, well, we have this parameterized algorithm, the configuration space we're going to denote with theta. And we have a distribution over problem instances, these training instances, with domain I. And we have a cost metric that assesses the cost of a configuration in theta run on an instance in I. And what we are looking for is a theta that minimizes this cost metric in expectation over instances sampled from this distribution D. So that's the algorithm configuration problem. Now, how do we apply this to planning? What can actually be parameters in planning? Well, some examples are, well, which heuristics do you choose? Subparameters of each of the heuristics are there. There's lots of parameters. And how do you combine the heuristics? That's a very important choice. Then there's some parameters in the search strategy, whether you actually use a global search or a local search, whether and how much randomization you use, and how to combine these various search strategies. And as we'll see, you can even optimize things such as the domain model encoding and the problem model encoding. More generally, when you think about what could be a parameter, it's really any design decision for which you have more than one alternative. And parameter types that are typical in algorithm configuration are Boolean, categorical, integer, and continuous parameters. And there's also this concept of conditional parameters that are only active dependent on the setting of some other parameters. So in this case here, the subparameters of a heuristic h are only active if that heuristic h is actually active. So if the Boolean parameter deciding whether this heuristic is on or off is on. And that actually gives rise to a structured space with sometimes multiple levels of hierarchies that, well, can also be pretty high dimensional. For example, in this case of LPG, we have something like 62 parameters giving rise to more than 10 to the 17 different configurations. And that is the reason that we actually call this algorithm configuration rather than just parameter tuning. So algorithm configuration is a really useful abstraction. It has improved algorithms across many different areas of AI, such as in satisfiability solving, mixed integer programming, the most probable explanation problem, timetabling, and most important to you, of course, AI planning. And in particular in AI planning, I'm listing 4 different applications here of configuring fast downward, LPG, and then also the domain model and the problem model. And for each of these, I will actually have a slide later on to give you some more details. Before that, however, I'd also like to mention that algorithm configuration is also a key enabling technology in automated machine learning, AutoML, for example, enabling tools such as AutoWeka, AutoSKLearn, and AutoPyTorch. And AutoML is actually where I spend most of my time these days, so it's really refreshing to be talking to the planning community for a change. All right, algorithm configuration is a useful abstraction that is also reflected in it being increasingly popular and increasingly used. And so here's, for example, the citation numbers for the 4 most popular algorithm configuration tools, and we see a nice increase over time. There's various different algorithm configuration tools. So iterated phrase is based on sampling. So it's an estimation of distribution approach. GGA and GGA++ are genetic algorithms. ParamLS is a local search algorithm, and SMAC is based on Bayesian optimization. And if you'd like to use several of these different packages, then I would recommend doing so through the AC-lib interface, which implements all of them. And my own empirical evaluation of methods in AC-lib shows that SMAC is actually very competitive, and that's why I'll mostly be talking about SMAC today, also in the interest of time. For you in AI planning, it might be most interesting to look at these rows, where, for example, well, this was a default performance of an algorithm, LPG, and SMAC found a much lower, in this case, runtime than ParamLS did. And so if you've used ParamLS before, I would encourage you to also have a look at SMAC. Typically, is giving me better results. So what is SMAC? At a high-level overview, SMAC works as follows. So it runs some runs of different configurations on different instances, and then at each step learns a model from this performance data that maps from a set of a combination of a pair of a configuration and an instance to the predicted runtime. And then it uses this model to select promising configurations. It compares these promising configurations against the best configurations so far by executing new algorithm runs, and then iterates. So after it has executed these new algorithm runs, it updates its model and continues. And the initialization is done by executing some runs and collecting the performance data. So that's a high level. And well, how is this model used to select promising configurations? Well, that's precisely the Bayesian optimization approach. And in ParamLS, that would be the local search, in GGA, the genetic algorithm, and so on. So Bayesian optimization, what is it? In a nutshell, it's visualized here. If you just have a single parameter and you have here its performance, and in this case here, we're maximizing performance. So this dashed line is a true performance, but we don't know it. We only know it at some points where we've actually run our algorithm. And what you then do is you fit a probabilistic model to this data, where this model should go through your data points or close to your data points, but far away from the data points, you're uncertain. And you have a mean function and predictive uncertainty, and you use this prediction in order to trade off exploration exploitation to look in regions where the predicted mean is relatively high, but the uncertainty is also high. So in this case, for example, here, where this is predicted to be pretty good, but could also be actually really good, you sample there and you see, oh, this was actually pretty bad. Then you update your model. So you see the model slightly changes here, mostly locally. And then you look again, okay, what's predicted to be high in mean and has a high uncertainty. In this case, you would sample here and you iterate this process over time until basically you're out of time. So that's Bayesian optimization. And well, I've skimmed over the details here, of course, but the predictive performance model we used is actually based on random forests here, which we've shown in some work before, works really nicely for actually modeling high dimensions with low effective dimensionality. So often you have a lot of parameters, not all of which matter so much, and you also have a lot of instance features, and you want to home in onto the important parameters and the important instance features, and random forests are very good at that, and they're also really stable and robust. So that's why we use them in Bayesian optimization. And then the next question is, well, we compare this list of configurations against the best configuration so far. How do we do that? Well, how many instances do we actually use in order to evaluate for each of these new configurations? If you used a fixed number of instances, n, that would be suboptimal. And here's a plot back from ParmILS, where we have here ParmILS, so basic ILS with an n equals to 100 instances. That's really slow. With 10 instances, it makes progress much faster, nearly 10 times faster in the beginning. But then teeters off a little bit here, whereas with 100, it actually gets better. And with 1, well, you actually really get, that's too noisy and you get overfitting, and you can actually get worse over time. So a fixed number is not good. Rather, we do this adaptively, both in this focused ILS variant of ParmILS and in SMAC. In particular, we start with n equal 1, so just one instance, and then reject aggressively. And we increase only the number of instances for good configurations. And we can actually prove that this is not hurtful to reject aggressively, but that we can actually come back to configurations that were unlucky in their first evaluation and picked an instance for the one instance for which they're bad, for example. So we can prove that when using this aggressive racing, the probability that both ParmILS and SMAC find the true optimal parameter configuration approaches 1. So that saves a lot of time over, for example, evaluating all instances. And we can save more time because poor configurations often take a very long time to solve a problem that the best configuration solves quickly, for example, an hour versus 1 second. And so we can actually cap this evaluation of the poor run after 1 second in this case, because we know it's not going to beat the incumbent. So we can safely discard this. And in the case of ParmILS, that actually provably doesn't even change the trajectory. And both in the case of ParmILS and SMAC, this doesn't hurt our theorem. When using aggressive racing and adaptive capping, we still have that the true optimal parameter configuration is found. The probability of that approaches 1. All right, so that is SMAC in a nutshell. We use Bayesian optimization with random forests to propose new configurations, and then we use aggressive racing and adaptive capping in order to compare them to the incumbent. And when they're better, then the incumbent changes, and the data that we've collected goes into the performance model and we iterate. All right, so before we go on, I just wanted to mention that really all of these components do matter for performance. So here's a case where I compare random search running on all the instances that are available, and that doesn't even make any progress over the default. In this case, well, that's for Cplex, but similar stats would probably hold for planning. So there's no improvement at all. When you then include racing into the mix, then you actually do make some improvement, also with random search. When you then include also adaptive capping, then you make more progress, but still Bayesian optimization compared to this random search is still over 200-fold, a 200-fold speed up. And well, larger speed up if you didn't have racing or adaptive capping. All right. So what I'd like to do now is to actually come true to my promise of giving you these details on these 4 different applications of algorithm configuration in planning. The first one of that is for configuring fast downward. So this is done by Chris Fawcett and also together with, of course, the Basel team. So, Aris Kapras is also on this. And Holger Hoos is Chris's supervisor. So the parameter space that they chose back then was basically focused on really which heuristics do you choose and how do you set their parameters. And these heuristics were then combined in an alternating fashion in a multi-heuristic greedy search. And there were also 8 additional parameters for the search. So in total, there were 45 parameters, more than 10 to the 13 different configurations. And this was configured domain-wise back then with focused ILS. And the results were that, well, you got nice speedups over the default version, very few instances where this would yield slowdowns. And so on average, 10-fold speedup. And per domain, sometimes no speedup, where you already had a good default, and sometimes up to 23-fold speedups. Right. The second application of algorithm configuration was actually at a similar time. Chris Fawcett was also involved in that, and this was led by Mauro Valati. And the parameter space that was picked here for LPG was, and LPG is a local search approach that works on a linear action graph. Basically looking for flaws in the plan and fixing them. So, for example, there's, of course, parameters about the flaw selection strategy, and then about the search neighborhood for the local search, the search strategy, pre-processing, heuristic functions, randomization, and so on. And so in total, that actually gave rise to 62 parameters and more than 10 to the 17 configurations. Again, configured with focused ILS. Again, relatively similar results, 10-fold speedups on average. And per domain, actually this helped for every single domain and sometimes also more than 100-fold speedups. And also, what this paper showed is that algorithm configuration can not only be used to optimize the speed of the planner, but also in the coverage, but also to improve plan quality. So there's 2 domains here, and these are basically the plots with the configured version, and here's the unconfigured version, and the configured version is much faster to achieve good plan quality, and in the end, it also has a much higher quality than the others do in the hand. All right, so next I want to talk about a work that I did actually together with Mauro. And here this is a little bit different. So this didn't just take one planner and configure that, but rather we looked at actually how to rewrite the PDDL file for any planner. So how can you actually write your domain model in a way that planners find easier to deal with, for example, because of tie breaking. And there's not that many choices you have in writing the PDDL file, but you can order your domain predicates, you can order your operators, and within each operator, you can order the preconditions and the postconditions. And depending on the domain, that gives rise to a different number of parameters. SMAC and ParaMLS can't deal with order parameters, so we hacked this as continuous parameter space. We basically said for each, for example, for each precondition of an operator, we gave it a continuous value, and then we just ordered these preconditions by this continuous value and coded up the parameter space like that. So there was up to 109 continuous parameters, and the results are, well, similar to before. On some domains or on some combinations of planner and domain, we didn't get any speed up, but it never got worse. And on some, we actually got up to 300-fold speedups. For example, here, YASP on depose, there was just no instance that took longer than 10 seconds, whereas with a standard domain model, there were actually many timeouts at 900 seconds. And one really nice thing that Mauro also did here is to use this automatically found information to extract some knowledge about the domain model. So what he did is use this functional ANOVA tool that we have for parameter importance, and that suggests to first list operators that are used often and that are, so we should first list these operators that are used often and that are used early in a typical plan. And we should also first list preconditions that are unlikely to be satisfied in order to avoid a lot of work being done to satisfy the first preconditions, and then you get to the last one, and that is typically not satisfied. You can save that work and first work on the preconditions that are actually the hardest to satisfy. All right, and then Mauro didn't stop at that. He actually continued and also did this for the problem domain model. So, for example, taking this original and configuring it to this one. Now, this is tricky. Of course, you can't just work on the problem domain model because, well, that would mean you actually need to solve that instance a bunch of times. So the problem model file. But what you rather need is a domain-specific heuristic that applies for all problems in that domain. So what he did is to construct a parameterized heuristic that uses features of all the propositional facts in the planning and coding graph. And then he configured the parameters of that heuristic with SMAC and the 26 parameters, and he got speedups up to 39-fold. And again, he used this analysis to figure out some general recommendations. So what he recommended is that the ordering of the facts in the initial state and the goal states should be aligned, and recommended that you should first list propositional facts that often occur in preconditions and that often occur positively. And finally, also to first list propositional facts that are most connected in this planning and coding graph. All right, so that was a bunch of different applications of algorithm configuration, and I hope to have convinced you that this is actually really a robust tool that can be used in many different applications to optimize your planner performance. Now, I want to switch gears and actually go to algorithm portfolios, which have a very different purpose. So algorithm portfolios are motivated by the fact that no single algorithm or parameter works best everywhere. They rather exploit the complementary strengths of these different planners or parameter settings in order to do well everywhere. And there's different types of algorithm portfolios. There's algorithm schedules, and these are actually very popular in planning. The first work on schedules dates back more than 2 decades to Adele Howe's work back then. And also the fast downward stone soup planner has been very successful over the years and has showed over and over again that there is just no single planner or no single approach that works best everywhere, and that we need to get the best of all worlds in order to get general good performance in many different domains. Another type of algorithm portfolio is algorithm selection, and that actually hasn't been all that popular in planning. It's much more popular in SAT solving. But there has been this one planner over the years that's called ICAPS, and what that does is actually a per instance selection of some top algorithms, and they are actually still combined in a schedule. And so there's some more recent work on algorithm selection, but I first want to talk about some features that you use in algorithm selection in order to actually make this possible. So if you have these features for planning tasks, then you can, of course, say, well, I've seen similar planning tasks before, and for those, this and this and this planner were good, or you can predict the runtime. So how can you characterize this fingerprint of a planning instance? That was the question we looked at back then in a paper with Chris Fawcett as first author, and we came up with 311 different features from different categories. So we used the PDL features by previous features by Roberts et al. Then some features from the translation to a finite domain representation, some graph-based features from the causal and domain transition graph that were actually from Sinamor et al. From this EBACOP planner. Then some pre-processing and LPG, sampling and torchlight, some probing features and fast downward. And I've highlighted this because probing features is something that you can actually just really pretty much run in any domain that you tackle. You just run some algorithm for the type of problem at hand and see and extract some statistics from its short run. And that is actually a type of feature that works really well here in planning, but also in other types of applications. And likewise, the success and timing features. You can always check whether your feature is computed or not and how long it took to compute these feature times. And you can use that as a feature itself. And so then there was also SAT representation types features. So overall, the takeaway from this work was that that more features typically led to better results. In particular, if you used random forests, and these are the same types of random forests we use in SMAC because, well, they can actually select the most important features, and in SMAC also parameters. And so here, if you put in some features that aren't actually that useful, it doesn't hurt performance. So you may as well put in a lot. So there are these features now. And with them, of course, you can do more algorithm selection. But actually, in the meantime, there is also deep learning approaches for algorithm selection, in particular in this Delphi planner by Katz et al. And later published at AAAI this year by Sievers et al. What they actually did is to compute an abstract structure graph and then basically take a picture of that and use that with standard convolutional neural networks from deep learning that are known to work well with images. And that actually worked very well, and well, they actually won the IPC with this. So yeah, it did work. But then in follow-up work, actually, Freiburg and Sipe showed that simple machine learning techniques actually perform similarly when you use the same graph. So when you take that graph and take statistics from it, such as, well, how many nodes are there, how many connections are there, and so on, then actually simple machine learning techniques suffice. So you don't actually need deep learning once you have that graph. But then again, if you do deep learning really well and you use graph convolutional neural networks that are nowadays the best types of deep learning techniques for graphs, then you actually do better again than the CNNs. All right, so much for algorithm selection and planning. There's actually also a lot of work outside of planning on algorithm selection. In particular, already back in 2015, what we did is to collect a design space of a lot of different algorithm selection techniques, such as multi-class classification, pairwise cost-based classification, such as in Zazilla, or hierarchical regression, just in earlier versions of Zazilla, different types of nearest neighbor approaches and clustering approaches, and then all of the different hyperparameters. And we use SMAC in order to find the best instantiation of each of these. And actually in this icon challenge on algorithm selection that had algorithm selection tasks from all kinds of different problem areas, this AutoFolio approach actually won the categories of the number of solved problems and the penalized average runtime score. So this is a nice thing. If you don't know which type of algorithm selector to use for your data, this might be actually an easier approach. All right. So we talked about algorithm configuration and we talked about portfolios. And these two have really opposite strengths. So algorithm configuration is good at finding great configurations for homogeneous instance distributions, whereas portfolios are good at shining for heterogeneous distributions, for taking these inputs. So it doesn't give you new configurations, but it makes sure to use the right one for the new instance at hand. And there's different ways that these two can be combined to get the best of both worlds. You can combine algorithm configuration and algorithm selection. For example, in this approach ICAPS, which first clusters the instances and then uses algorithm configuration for each cluster. or in this Hydra approach that uses algorithm configuration to search for the configuration that maximally improves an algorithm selector. Likewise, you can combine algorithm configuration and algorithm schedules. And for example, Seip et al. Used algorithm configuration for several planning domains and then combined the result into a schedule with uniform timeshares. And in a follow-up work that we did together with Jendrik, that was more similar to Hydra, but for schedules where we searched for a configuration and a time slot for that configuration to maximally improve the performance of a schedule. All right, so you can already get the best of both worlds of configuration and portfolios with these approaches here. But what you can't do is react to the state of the algorithm. So from what's going on, search progress, am I making any progress on this planning instance or not? It would be really nice to actually react to that and change our parameter settings dependent on that. And so that's what we want to do with dynamic algorithm configuration. So which planning parameters could we actually adapt? We've seen different case studies of using algorithm configuration. And in blue here, I highlighted the parameters that would actually make sense to adapt. So heuristics definitely makes sense to adapt over time, and I'll show an example of that. The search strategy definitely makes sense, and I'll also show an example of that. And local search parameters tend to always help if you change them over time. The one that doesn't really make sense to adapt over time is the problem encoding, domain model and problem model, because, well, you do that once in the beginning. You could, however, think about restarting your algorithm and then using a different domain model or a different problem model in the restart. And then, well, when you restart and with which different models you restart, those would, of course, then be adaptive parameters. And the other day, I also talked to Malte Helmert about this. What are the planning parameters that you think could be adapted? And he said there's just really a lot. But what this community might actually be excited about is to think about merge strategies for merge and shrink to adapt those and to actually configure them in the first place. And also in general, when to do something. So for example, when to derive a new heuristic or when to discard an old one. If that can be made conditional on certain state features, that could actually be really useful. All right, so there's lots of planning parameters to be adapted, and let's see how we do that. But before that, I do want to mention that we're definitely not the first ones thinking about reacting to state. There's actually this really cool early pioneering work by Lagoudakis and Littman that goes back almost 20 years, where they basically had state-specific algorithm selection here for a sorting algorithm, and then for branching rules in DPLL for SAT. And they used really very similar techniques as we would use nowadays. And of course, the state of reinforcement learning wasn't quite as far. And actually, when I started my PhD, I consciously decided not to go down this road, but to rather stay with algorithm configuration and some algorithm selection, because those were much clearer defined problems. You didn't need reinforcement learning. It was just optimization basically for algorithm configuration and just supervised learning for algorithm selection. And reinforcement learning was, I found not well developed enough back then. And nowadays, there's been so much progress in reinforcement learning. I think now is really the right time to tackle this problem in its full generality with DAC. Again, we're not the only ones thinking about this. Also for planning, there's really cool work by Pavel Gomoloch and colleagues. Last year at ICAPS, they had an approach to learn to switch between different search methods. And this year, they had a black box optimization of a neural network controller that would adaptively parameterize a mix between global and local best first searches. So there were 6 parameters that would be adapted over time, and based on quite interesting state features. So this is definitely an example of what I would call DAC. So what is this DAC? We talked about algorithm configuration formally. Now let's also formally introduce duck. And you see a very close resemblance between standard AC and dynamic AC. The two really differ in, well, there's this cost metric assessing the cost of a configuration here, and here it's a policy. And, well, what is this policy? This policy, well, looks at the state and the instance and then spits out a configuration, and that adaptively. So over time it changes, and this policy can be evaluated just like a configuration can be evaluated during rollouts. You can formalize this duck problem as a contextual Markov decision process, where basically, well, you have your little agent and it gets a state feature from your algorithm, applies some action. So in our case, it means set the parameters to a certain value. Then you run the algorithm for one step with these actions, and then maybe you get a reward for that action, and you get a new state. And you don't only do this on one instance, you can also do this on multiple instances, and that's where the MDP becomes contextual. So contextual MDP is a set of MDPs, M sub I, where each M sub little I is an MDP that, in this case here, shares the same state space and shares the same action space, but has a different transition function and potentially a different reward function. All right, so that's a formal definition of duck. Next, let's look at some of its other properties. Something that's really nice and that I've hinted on is that it strictly generalizes all the different formulations we've seen so far. So for example, algorithm configuration just gives you a static configuration. And you could, of course, mimic that with duck by simply not looking at your inputs and just always outputting a fixed configuration. Likewise, selection picks the right algorithm for a given instance. And again, you could just look at the instance and pick the right algorithm. And the space here of configurations is strictly is a strict generalization of the set of algorithms, because you can just have a single parameter that is categorical that has all these values, so all these different algorithms in there. And then, of course, you could do more cool things, such as all the parameters of all these algorithms. So this is strictly more powerful. The same applies to schedules. There you look at the time. Here you could just look at the time and not the others, and so on. And this naturally gives rise to this proposition that the optimal duck policy is at least as good as the optimal solution to any of the above. And what's slightly more interesting is that actually the optimal duck policy can also be exponentially better than the optimal selector or the optimal schedule. And we'll see in a bit more detail what that can look like later. Before that, I want to first tell you why I have hope and that duck might actually also be a useful abstraction, just like I showed before that standard algorithm configuration is a useful abstraction. So we have 3 papers on duck this year. The first one actually did a lot of experiments on white box and toy benchmarks to test the boundaries of duck. The second one actually looked at controlling the continuous step size in CMAS, an evolutionary strategy. And then the third one is on AI planning. So what we did in the first one is to actually look at generalization across instances, and that can actually be really strong. We looked at scaling with a number of parameters that was okay. So up to 5 parameters can be good. If there's strong correlations between them, then it gets somewhat harder. And we had a task that really required using both instance features and state features, and there duck also did find the optimal solution. In this problem here, for looking at the continuous step size of CMAS, we had available already an existing heuristic for updating the step size in CMAS, and we showed that you can use guided policy search in order to actually learn from that teacher and then learn to be better than that teacher. And that would be a lot more sample efficient than without a teacher. And then this last work for AI planning, well, that I'm going to tell you in a bit more detail now. So in this work, and that was just at the PRL workshop here at ICAPS, the setting is as follows. So the planner thinks about what state should I expand next, and it has access to different heuristics. And all of these heuristics say a different state would be best. And the planner doesn't know who's correct, so he asks our RL agent, Mr. Duck. And that hopefully tells it the right state to expand. So much the comic version. So the basics here is we're in the setting of satisficing planning. We're searching for a good plan, and we know that inadmissible heuristics are actually difficult to combine. So if we just chose the max of the different heuristics, then if we have one bad heuristic that says infinity, then everything is infinity, and we're dead in the water. So rather, what we do is greedy search with multiple heuristics, where we have one separate open list for each heuristic. And at each step, each heuristic is evaluated. So the setting is not that we select which heuristic to evaluate, but it's what we select is which open list should we pick from. There was this paper by Gabi and Malte in 2010 that showed that actually this alternation strategy can be better than any single heuristic that is being combined. So not putting all your eggs in one basket, but alternating between these different heuristics and picking one open list at a time in a round-robin fashion could actually be really good. And the question we asked ourselves here is, can we do better than alternation with a duck strategy? And theoretically, the answer is a resounding yes. So for each algorithm schedule, not only for this alternation strategy, but for any that just looks at time, and for each algorithm selector strategy too, there exists a family of planning instances, a collection of heuristics, and a dynamic control policy pi-duck, so that greedy best first search with a set of heuristics and this policy pi-duck expands exponentially less states than greedy best first search with the same set of heuristics and the schedule or the selection strategy. So that's cool. The question is, does this also empirically work out, or is this only a theoretical result? And that's an empirical question. So we used reinforcement learning, of course, and here's a setup for that. So the action space in this experimental setup was we had 4 different heuristic functions to choose from. And the state space we used was we had a time step, and we had really simple features in our state. So just really for each of the open lists of each considered heuristics, we only looked at the max, the min, the mean, the standard, the variance, and how many elements are at that open list. And we didn't actually use absolute values, but we used the difference between these features between consecutive time steps. The reward we kept as simple as you can think, just -1 for each expansion step in order to find short plans. And the RL strategy was also quite simple. It's an epsilon greedy deep Q learning with a double DQN and with a relatively simple feed-forward network with 2 hidden layers of 75 units each. And the experiments was when we did domain-wise training on 6 domains with 100 training and 100 test instances each. And lo and behold, we could actually show that our RL agent did better than the alternation strategy, did better than all the individual heuristics. Well, the alternation was much better than the individual heuristics, also better than the random. And we're also better than the best possible algorithm selector. So this is not just any algorithm selector, like one from the competition or so, but it's really the best you can do given that you can only choose between these 4 different heuristics. And so this alternation strategy is roughly as good, and this RL approach is actually better than the Oracle. And then that's kind of cool. All right, so I'm nearing the end. And I just want to point out a few more things that we're doing in the realm of Duck, and then some opportunities that I see for planning folks to actually join forces. So one thing that we looked at is that actions actually often need to be repeated many times in Duck. And so what we do is really we learn when to act. And we have this tempo RL approach that basically uses hierarchical reinforcement learning to pick an action and then pick how long to repeat this action for. And that can substantially improve the sample efficiency of the approach. And then also at runtime, you don't need to query quite as often. So it can also run faster. the next thing that we're currently looking at is an active selection of instances that are helpful in learning. So using a self-paced reinforcement learning approach. In self-paced reinforcement learning, we actually have the value function, and we're making use of this value function for each instance to look at for which instance is a value function actually changing right now, where are we currently making progress, and we're preferentially using those instances where we're making progress, rather than any instances that we're solving all the time already really easily, or instances that we can't solve at all yet. And then finally, we're currently creating a library of DAC benchmarks using a simple format, the OpenAI GIM format, and we would really love to include any DAC problems that you can come up with or that you have. And that brings me to ways in which I think planning experts could be getting involved in DAC. So the first one is really choosing the right problem. Where do you think DAC would be most likely to actually help, and which parameters are crucial to adapt? You know this, I don't. So it'd be great to talk about that. The second one is to constrain DAC to simple strategies to actually aid interpretability and learn something about what's going on. And also what I think will be important sooner or later is to combine algorithm configuration and dynamic algorithm configuration. So configuring many static parameters, and then only some of them need to be dynamically adapted. The second way in which I see planning experts come in is in instance features. So we actually have these good instance features that I talked about, but we don't actually use them yet. And these might actually directly allow for domain-independent planning by DAC. Probably this needs a bit more work, but I think this is definitely really exciting. In terms of state features, we really only had a very first shot at these. So better state features, I think, will definitely improve domain-specific and domain-independent planning. And this is something that also came from this discussion with Malte. What he said is really something that I'd like is something that looks at the whole log file of fast downward and then tells me what to do. Because, well, this is something that Malte can do himself. He can look through this log file and figure out what's going wrong. And then he can have a good hinge on what heuristics should be used next and so on. And, well, if Malte can do this, then it might be possible to actually, well, gather a lot of data and then train some interesting neural network. For example, using transformers or so to parse this would be very cool. I think this is definitely not to be solved next day, but I think this is a cool vision to have, and I think we will get there at some point. And the final set of opportunities I see for planning experts is to actually generate insights using these data-driven tools. So use algorithm configuration and DAC to improve planner performance, but then use meta-algorithmic tools to understand why this performance improved and use these gained insights to develop new and better algorithms. I think that would be really cool because in the end, we all care about making better algorithms and understanding things as scientists. For algorithm configuration, we actually do already have automated parameter importance analysis methods. So something that does forward selection to pick the right, the most important parameters and features, ablation analyses that tell you what are the most important parameters to change from the default value, functional ANOVA that quantifies how large the share of the variability in a function is by changing the different parameters, and also quantifying the interaction effects between different parameters. And this is actually the tool that Mauro Vallati used in this domain configuration and the problem configuration, so kudos to him. And we also have a nice framework that actually generates automatically generates reports that make all of this algorithm configuration stuff a little bit less black box. For DAC, we don't have this yet, and it would be great to actually develop this. Maybe we can develop this together. And so one thing I think would be interesting there to look at is, can we have strong yet complex policies be approximated with simpler ones? And there I'd like to give another pointer to this work by Freiburg and Seib, who did something similar for algorithm selection. So I think if we could do something like that for DAC and understand what are the policies that we're learning, that would be really cool. Right, with that, let me conclude. Algorithm configuration is a reliable workhorse. It has often led to speedups of orders of magnitude. And then DAC that's a new kid on the block. It's a strict generalization of algorithm configuration and selection and schedule, so it's really powerful, but it's also much harder. It's in this reinforcement learning setting, and we have first success stories, but it's still at an early state, and I would love if you could actually help us in making Duck a great thing for the community. So try Duck, break Duck, and improve Duck. And yeah, we're building a team of postdocs on Duck in Freiburg, so if you're excited by this, then, well, give me a call or an email. And if you have awesome graduating students, then, well, let them know too. With that, thank you very much, and I'm looking forward to a lot of cool discussions. Thanks.